Hi there, Mr. Sutton with the AB Calculus 6.5 homework solutions on exponential growth and decay. On this problem, we have atmospheric pressure decreasing approximately exponentially as elevation increases. If pressure is 772.8, this is mercury, millimeters of mercury, in a valley 0.2 kilometers below sea level, and pressure at sea level is about 754.0 millimeters of mercury. We want to know the pressure at 3.1 kilometers above sea level. All right, well, let's start with our formula. Since it's exponential and they're telling us pressure decreases exponentially, we're going to use our exponential decay formula, y equals CE to the negative KT. Ultimately, the input to this is, let's see, the input is elevation, the output is pressure. So in this scheme, y represents pressure, as does c, and then T is going to be the elevation in this case. Now, ultimately, they want to know what is the pressure at 3.1 kilometers above sea level. So ultimately, we're trying to get this Y value here. And we're eventually going to be plugging in 3.1 kilometers for the T value. But we also need the K value. Do we need the C value? Well, they didn't actually, let's see, the pressure at sea level is 754, so we've actually got the C value here. That's the pressure at sea level. So the only thing we're missing is this K value. In order to find K, we're going to have to solve another one of these equations first. We're going to need Y, C, and T to solve for K. So what we're going to use is this other value of pressure at a different input value. And we're going to use this to solve for K, which we can then turn around and plug in to get the true Y value. So for my first equation, I'm going to set up my target Y value, my target pressure is this 772.8. My C value, my sea level pressure is 754, and that's going to be true for the whole duration of the problem. And then we're going to be doing e to the negative k, because we're still solving for k, times a t value of, well, that's this 0.2 kilometers below sea level. That's this other elevation. Since we're below sea level, I'm going to plug in negative 0.2 for that. And now I just have to solve for k. All right, well, let me divide both sides by 754 to get this exponential piece by itself. And now I can just get those negatives out of there and call this 0.2k. Next, to get this out of exponent land, let me take the ln of both sides. That gets rid of the e. And now I just have to divide both sides here by this 0.2. So let me go ahead and do that on Desmos. Clear out whatever else is in there. So we've got fraction, ln, parentheses, and then we've got 772.8 divided by 754.0. Close the parentheses, go down to the lower level of this fraction, and I'm going to divide by this 0.2. And that's coming out to about 0.123 and some change. So what I'm going to do here to save that value, because I'm going to need it for later, I'm actually going to arrow back to the beginning, and I'm going to say A equals all of that. And you could choose any letter you want, but I'm going to use A. Now I've got that stored. And I'll just write down what I did here as well. So I've got K equals this A value of about 0.1231, etc., etc. Now that I've got my K value, I can plug that in along with my C value and my T value here of 3.1 in order to get the value they actually wanted, which was the pressure at 3.1 kilometers above sea level. So I can write Y equals 754, that's still my initial value there, times E to the negative, and now I've got A times the T value 3.1. And actually I don't need the negative anymore. Or do I? Actually, I think I do. Yep, that's part of this exponential decay thing from the beginning. We haven't really changed that. We've just come up with a k value and a t value. So yeah, let's leave that negative in. All right, let me run those numbers on my calculator. So I'm going to do 754 zero point 0 times e exponent, and we'll do negative a, which I had stored, parentheses, times 3.1. And that comes out to about 514.739, and the output here is going to be millimeters of mercury. Whoops, there we go. Just adjust those decimals a little bit. Now we're good. For this problem, we have an island's population growing at a rate proportional to its population. Population quintuples in 73.2 years. In how many years will the population triple? Well, we know it's probably going to be less than 73.2, but beyond that, we're not really sure. So since I have this population growing at a rate proportional to the population, that's code for exponential growth in calculus land. So we can use y equals ce to the kt to deal with this problem. And ultimately, we want to know in how many years the population will triple. So when the y value is 3 times whatever the c value is, we want to know what the t value is. Unfortunately, I would also need to know what k is in order to figure that out, and I don't yet. So in order to get the k value, I'm going to use the other piece of information about our population quintupling in 73.2 years. So initially, I'm going to set up my equation so that I'm replacing y with 5c. That represents quintupling the initial population. And I'll leave c the way it is. So whatever c is, I've got 5 times that over here. And then I'll have e to the k times 73.2. I can use this 5c if I use 73.2 as my time, because those were linked in the problem. Now, in order to get the k value, I need to divide both sides by c first. That'll give me 5 equals e to the 73.2k. And then if I take the ln of both sides to get this out of exponent land, I've got ln of 5 equals 73.2k. Next, I just need to divide both sides by 73.2. So I'll just do that on Desmos here. We've got ln of 5 divided by 73.2, and we get this random number here. Now I am going to store that as a variable. I'll just store that as a, so I'll just write a equals, and now I've got my k value stored, and I can just use a instead of this crazy thing whenever I need to. And I'll just write that here as well. So a is approximately 0.02220, but I'm just going to use the true value off of Desmos. Now that I've got my k value, I can go back to my original formula and plug that in for k. So I want to know in how many years. So this time, since we're tripling, I'm going to use 3c for y instead of 5c. So we're going to have 3c equals c times e to the a times t, because my k value is this a value I stored. Let me go ahead and solve this for t now. Divide both sides by c, so we've got 3 over there. Take the ln of both sides, so I have ln of 3 equals at. And then dividing both sides by a, I need to go on the calculator for that. So let me go down here. ln of 3 divided by a comes out to about 49.967. And that is going to be in years according to the what the population's time units were. For this one, during the exponential phase, E. coli is increasing at a number at a rate proportional to the current population. So we have exponential growth. We can use y equals ce to the kt for whatever we do in this problem. And if the growth rate is 1.6% per minute and the current population is 188.0 million, what's the population 9.1 minutes ago? All right, so ultimately we need to get this y value here, and we're plugging in things for c, k, and t. So for c, that's the initial population, 188.0. And we have e to the k value of, well, we have a growth rate of 1.6%. So as a decimal, that's 0.016. And then for the t value, they said 9.1 minutes ago. So we need negative 9.1. And now I just need to crunch all those numbers on Desmos. So plugging all that in, we got 188.0. We don't really need the 0.0, but whatever. E exponent 0.016 and parentheses to multiply negative 9.1. Comes out to 162.527, and that's going to be in millions of bacteria. For this problem, we have atmospheric pressure decreasing exponentially as elevation increases. Since we have exponential decay, I'm immediately going to write y equals CE to the negative KT, so I can use that. Now they're telling us if pressure is halved with an increase of 5.9 kilometers, what's the rate of decrease? So we're going to be solving for this K value here, which means I need to plug stuff in for Y, C, and T. So for Y, that is like the new pressure. We don't know what the old pressure was, though. They didn't tell us that. But we know that the new pressure is half of the initial pressure. So for my Y, I'm going to use 1/2 C. And I'll just use C for the initial pressure since I don't know what it is. For the T value, we're going to use 5.9 because that is the elevation increase in the problem. So we have negative 5.9 K in that exponent with the E then. And at this point, I just need to solve for K. So I can divide both sides by C. That gets me just 1/2 over on the left. And now if I take the ln of both sides, I've got ln of 1/2 equals negative 5.9 K. And then let me just divide both sides by negative 5.9. So doing that on the calculator, let me make a fraction, ln parentheses 1/2, close that, and negative 5.9 down there comes out to about 0.117 if I take it to 3 decimals. Expressed as a percentage, we can just move this over 2 decimals to get 11.7%, and that is the percent decrease per kilometer.
For number 5, not a whole lot of work, but a lot of interpreting on this one. So the rate of change of volume of a tank with respect to time is directly proportional to the square root of volume. Which of the following differential equations describes the relationship? So let's break this apart piece by piece. We have the rate of change of volume with respect to time. So that's going to be dV over dt. That's how we can express that, which right away gets rid of choices A and B. So we're looking for C, D, or E. Okay, is directly proportional to something. So that means we have some constant K getting multiplied by something else. And then, what's it directly proportional to? The square root of the volume. Well, how about just square root of V? Looking at our answer choices, that describes choice E. For number 6, we have a rumor spreading among a population of n people at a rate proportional to the product of the number of people who have heard the rumor and the number of people who have not heard it. If P is the number of people, which differential equation can model this situation with respect to T, with K being a positive constant? So we haven't seen this yet in the curriculum, but this is actually an example of something called logistic growth. But you don't need to know that to do this problem. So we're going to have dP over dt, which all the answer choices have anyway, equals, and they said that this is a rate proportional to the product of the number of people who've heard the rumor. So if it's proportional to the number of people who heard the rumor, we've got K times P. Proportional to always means we have K times something, and P is the number of people who have heard the rumor. So we've got the product of this and the number of people who have, where are we? Right here. The number of people who have not heard the rumor. Well, how many people haven't heard the rumor? There are n total people. If P of them have already heard the rumor, that means that n minus P of them have not heard the rumor. So this is the setup we're looking for here, and that would be answer choice B.
On this problem, we're told the population of a city is growing according to the differential equation dP over dt equals Kp. So this is proportional growth expressed in a differential equation. This is exponential growth that we're dealing with here. And they told us the city doubles every 12 years, so that's also exponential growth kind of language. So in order to do whatever I'm going to do on this problem, let me use the formula y equals CE to the KT, basically our PERT formula from pre-calculus days. Okay, so now they want us to find the value of K. K is this constant here in this formula. So that means we're going to have to plug in values for Y, C, and T. So Y is the new population. We don't know what the original population is, but we know that it's doubling every 12 years. So I'm going to use 2c for this y value here, and c will be the original population. Now for the t value, this 2c happens every 12 years, so I'm going to use 12 for t. So this is going to be e to the 12k. And now if I'm just solving for k, I can divide both sides by c. That'll give me 2 over there, and then if I just take the ln of both sides, I've got ln of 2 equals 12k. And then I just need to divide this by 12. So for that, I'm going to go to my calculator. I'm just going to do ln of 2 divided by 12, and that comes out to about 0.058. I'm going to round this to 3 decimals and pick my answer choice, so that's going to be choice A.
For number 8, bacteria in a certain culture increases at a rate proportional to the number present. So immediately we're talking about exponential growth, and we go right to y equals ce to the kt. Now, if the number of bacteria doubles in 3 hours, in how many hours will the number triple? So we need to figure out, eventually we need a t value out of all this. But before we can get that, we need to know the k value, a y value, and a c value. So to get the k value, they told us that the number of bacteria doubles in 3 hours. So that means when time equals 3, we can use 2c for the y value. So we've got 2c equals ce to the k times 3. And to solve this, we're going to have to ln both sides to get this 3k out of the exponent. So we have ln of 2 equals 3k. So k then equals ln of 2 over 3. Now this was a no calculator problem, so you really just had to leave it like that and hope for the best. Moving on, we're going to now plug in k, ln of 2 over 3 for k, and we also want to know eventually what the t value is. So this time, what are we using for y? Well, we want to know in how many hours the number of bacteria will triple. So now we're going to use 3c for y. And again, we're going to have ln of 2 over 3 plugged in for k. And this time we're solving for t. So we can ln both sides again. That's going to be ln of 3 equals ln of 2 over 3 times t. And now to get t by itself, we have to multiply both sides by 3 and divide by ln of 2. So we end up with 3 ln of 3 over ln of 2 equaling t. And that's going to be choice A. For number 9, we have the weight of a population of yeast given by y, measured in days for t, and the weight is increasing according to this differential equation, dy over dt equals ky. And k, of course, is a constant. So given that at time 0, the weight of the population is 120 grams, and increasing at a rate of 24 grams per day, we want to know which expression could represent that original function. So right away, when I see this differential equation, I'm thinking, yeah, this is going to be exponential growth. That's what this means to me. So I'm going to go immediately to y equals ce to the kt. Now, looking at our answer choices, there's only 2 answer choices that are in this format, A and B. So C and D, I mean, C kind of, sort of, maybe, I don't know, might be this, but probably not. And D definitely is way off in left field. So now I have to figure out my C value, my K value, and T is going to remain a variable when all is said and done. For the C value, they said at time 0, weight of the population is 120. So that's our C value then. That narrows it down to answer choices A and B. But in order to find the K value, I mean, how could I find that? One thing you could try is plugging 120 in for C, and then they said at time 0, so I'm thinking, well, maybe if I use 0 for T, but then I still need to find something for the output at that time. But the output, it's also 120, so this is kind of confusing. In order to actually get that K value, you need to go back to the differential equation, because they want you to use this rate of 24 grams per day. And the only place where we have a variable to represent that is in the differential equation here. That's the dy over dt. That is the 24. So we can say 24 equals K times the y value, 120. And no calculator, so we have to divide by 120 and reduce it. That reduces to 1 over 5. And now I can plug in 1/5 for k. So I'll have y equals the initial value of 120 times e to the 1/5 t. And we can write that as t over 5, which gives us answer choice B.